Well, I think that scientific computation is here since at least 100 years, or even more. From the beginning, I mean, Fourier started giving some basic concepts to compute the solutions of difficult systems. And then with the advent of modern computers in the 40s and the 50s, people have started simulating very big and complex systems. And they started to try to understand, for instance, the behavior of the weather climate. Or in the very beginning, they simulated the nuclear explosions. You know that scientific computation has been behind the conception of the nuclear bomb in the United States with the Manhattan Project. And since then, it has been evolving by occupying almost virtually all fields of science and technology. I think scientific computation is used today to design new products in any industrial technological environment, basically. So go from airplane to automotive, even in sport competition. I mean, we try to improve the performance of sport. Say, people are talking about the multi-objective optimization. So you try to optimize systems with the idea of having new products with better performances, or for instance, having a low impact in terms of noise or pollution. I think that in the future, the field will be, the most important field that will be dealt with scientific computation will be medicine and biology. So you try to describe the very difficult and uncertain systems which stem from human body. And you try to go from the macroscopic behavior, computing what's happening in the let's say, in the nervous system or in the biomechanical system, down to the cellular level. So there is this gap between the macroscopic description and the microscopic description, which is very appealing and very challenging for scientific computation. So I'm expecting scientific computing to be more and more relevant for the understanding of this very difficult field in the future. A very substantial activity that we have been carrying out is concerned with the simulation of the blood flow in the whole cardiovascular system. We try to understand how blood propagates, how the system reacts to some external changes. For instance, when you put a prosthesis, a stent or a shunt in a coronary, we try to understand how the flow field changes due to the presence of this external body, say. And you try to predict the different response of a specific individual to different kind of interventions. In this way, you are not forced to touch the patient. You just recompute the behavior in this virtual environment, which is the mathematical laboratory. You write down equations, and you try to use these equations to understand very complex mechanisms and hopefully to predict the outcome of new surgical operations.